Hello and welcome back everybody to our class in geometry. Today we will be looking at another aspect of the circle. In this case, it is what is known as the intercept arcs and also inscribed angles. So they are related to each other. So we're going to look at those and see how does that play into all the stuff that we've been learning about the circle. So here we're going to go ahead and define a few things first just to get started. The first one is going to be what is known as an inscribed angle. So an inscribed angle is in an arc if the vertex is on the circle and the side contains the chords of the circle. So here you can see two examples of where you have two angles where, as we said, the vertex is going to be on the circle itself. And then if you look at each of the sides, they are going to contain the chords that are going to be inside the circle then. So both of these guys are examples of inscribed circles. Now, in each of those inscribed angles, you can see that there is an arc over here, and then there's an arc over here. So that is basically what we're looking at in the next part. An angle intercepts, and that's the key word over here, an arc if the ends of each arc lies on the angle. Condition number 2 is that all other points of the arcs are in the interior of that angle. And then finally, the last one, each side of the angle contains the endpoints of an arc. So both of those scenarios, you can see that those are considered the angle is considered intercepting the arc because it's inside the angle itself, and also all the points are in there. And notice that the endpoints are actually going to be on the angles. So here underneath, you can see a few more examples. In the first case, you actually have an angle where you can see that there are two intercept arcs right there. Now, note the first one is actually not an inscribed angle because the endpoint, the vertex, is not actually on the circle. So be careful about that one. The second one right here, this is actually considered something called a secant tangent because you have a tangent line, meaning that it touches the circle once, and then you also have a secant, which is basically going to contain a chord. But here, looking at the blue, don't look at the red part of it. That is going to be considered as an intercept arc because, again, it follows all three conditions. Now, the last one, unfortunately, that is not going to be considered an angle intercepting the arc because you'll notice that while the inside right here, that's all in the interior of the angle, unfortunately, you'll notice that the second side right here does not touch any piece of that arc. So therefore, it fails one of the conditions. So hopefully you can see the difference between the two and when you're actually going to have an inscribed angle and also when you have the intercept arc. Now here, let me go ahead and scroll down to this. So then that way you can kind of combine the two together to see some of the things that are pretty interesting. You'll notice that we have 2 points right there. Maybe we'll go ahead and call one A and then the other one B. Now, from there, what I can do is go ahead and create some inscribed angle, and here's what you can see, or hopefully you can notice it. So here, if I create one inscribed angle, that's one of them. And then for another one, we'll go ahead and create another inscribed angle, maybe over here, right? And then you can create another inscribed angle, maybe like say over here. And then you basically have a whole bunch of inscribed angles that you can create, and maybe this one right here. And you'll notice that one thing that is kind of unique about it is that each one of these angles right here, they definitely look like they are congruent to each other. And in addition to that, they have a specific size that corresponds to the size of the arc that is created by them. So that means that there is a relationship between the two. And the question is, well, what is that relationship? And that goes into our theorem right here. So the theorem right here is called the Inscribed Angle Theorem, or IAT, I guess if you want to call it for short. And this is basically what it says, that the inscribed angle is half of its intercept arc, okay? The inscribed angle is half of its intercept arc. So going back to our previous example, that basically means that if you have a circle and then you have an arc right here, and let's say that arc is given to you as like, oh, I don't know, how about like say 90 degrees, then that means that the inscribed angle is going to be 45 degrees because that's the half of the arc right there. So that's the general idea behind it. So let's go ahead and see how the proof actually works. So this one is a little unique because we have to break it into 3 different cases. The first case is, what if we have the situation where, well, this is what we're going to have to kind of build off of. Case number 1, in this case, we have a side of the angle that contains the center. And so what that means is that AC right there, APC more specifically, that is going to be the diameter of the circle. Okay, so let's say that we have a scenario like that. Now, what I want to do is I want to prove that this angle BC, the measurement of this arc BC, is going to be twice this guy over here, which is going to be angle A. So let me go ahead and call this angle, we'll go ahead and use a new symbol right here. We'll go ahead and call it theta for right now, okay? Since BC, the measurement of arc BC is theta, then that means that the central angle BPC, that is also be equal to theta, because if you remember, the central angle and also the measurement of the arc is going to be congruent to each other. Now, what I want to do is I want to move theta inward into the piece that I want to solve for. Know that we have these 2 pieces, those are both radii and they're congruent to each other. So what that means is that the opposite angles are going to be congruent to each other because we have an isosceles triangle. So let's go ahead and call this one X, and let's go ahead and call this one X over here. So if we do that, then according to my exterior angle theorem, then that means that 2x is equal to theta. And so x is now equal to theta over 2, which is exactly what I'm trying to prove. So right there, that x right there is going to be half of the angle theta that we have. So that's case number 1, if we have an inscribed angle that is on the diameter. Now, case number 2 says, well, what happens if that doesn't happen? What if, like, say, the center is going to be inside the interior of the angle then? So case number 2, where the center is in the interior of the angle. Well, that one's not too bad because now we can build off of case number 1. Here's what we can do. We can go ahead and create a line segment, more specifically that chord that is going to be the diameter, just like in case number 1, and we will have 2 of those situations then. So here, we're just going to go ahead and create the diameter as we said. So this part right here, let's go ahead and call that x over here. So according to case 1, then this guy is going to be x divided by 2. And if I call this part y over here, then this part right here is going to be y divided by 2. And if I add up the 2 angles together, then you can see that angle A, the measurement of it, is going to be equal to x over 2 plus y over 2, which is equal to x plus y over 2. Whereas the measurement of the arc BC is going to be the sum of those 2, which is x plus y. So there you go. Once again, it's going to be half of the measurement of the arc. Now, the last case, you can probably guess it, is that, well, what happens if your center is going to be in the exterior of the angle then? Well, looking at case number 2, you might get an idea that, okay, we can probably do the same thing as case number 2 over there. And that's, again, build the diameter. But this time around, we're going to look at maybe instead of addition, we can look at subtraction. So let's say for the time being that the entire, well, actually, I need to give this part a name. Let's go ahead and call it APD right there. That's the diameter. So let's say that this part over here is going to be, oh, I don't know, how about angle, we'll call it, let's go ahead and use theta because we've been using that so far. So then that means that the entire angle over here is going to be theta divided by 2. Now, next after that, we're going to look at this part over here, and let's go ahead and give that one a name. And since we've been using fancy angles, let's go ahead and call that angle alpha, just so then that way we can, introduce some more of these variables that we don't normally use. According to case number 1, then that means that this angle right here, CAD, that's going to be alpha over 2. Now, if you look at what we're trying to solve for, which is the measurement of arc BC, that is going to be theta minus alpha. And then now we're going to compare that to the measurement of angle BAC, which is the inscribed angle in this case. And according to our picture, it's going to be theta over 2 minus alpha over 2. And that definitely looks like it's going to be half of what we're looking at previously. So there you go. All 3 cases, it's going to work out then in this case, okay? All right, so some characteristics that's going to be pretty interesting that might interest you are the following. Well, in corollary number 1, we kind of like showed an example of this already. So if you have 2 inscribed angles intercept the same arc, then those two angles are going to be congruent. So right now we can actually have that proof. That was basically going by the picture that we had. So here you can see you have 2 points, and if I create an inscribed angle right here, and then you create a different inscribed angle using those 2 points, then the result is that these two right here, they're definitely going to be congruent to each other. Okay. Now this one, corollary number 2, takes an extension of that. It says, now, if I have a quadrilateral that is inscribed in the same circle, then its opposite angles are going to be supplementary to each other. So that means that if I have this angle right here, we can go ahead and say, just to make it a little bit easier for us, let's go ahead and say that this guy right here is going to be equal to 80 degrees. Okay. Now, according to what we just proved, right, using the inscribed angle theorem, then that means that the measurement of the arc from here all the way to here will be twice as that, and which is going to be equal to 160 degrees. And looking on the opposite side, if you know that that portion of the arc is at 160 degrees, then the opposite portion over here is going to be 360 minus that. So 360 minus 160 degrees. And the reason is, well, a full revolution is 360 degrees. So if you subtract the missing part, then you're going to get this piece right here. Well, now we can go ahead and use the IAT once again to say that this guy over here, that's going to be the inscribed angle, and that should be half of 200, which is going to be 100. So now you can see the relationship right there. As it says, they are supplementary to each other. And finally, for the last part over here, for this corollary, for the third one, now this is probably the most interesting one because it's going to most likely carry over to trig and also calculus. If you have an inscribed angle that contains the semicircle, then the angle is a right angle. So remember, a semicircle means that you have a half a circle. So that tells you that the measurement of the arc is equal to 180 degrees. Well, if that's 180 degrees using IAT, then that means that this angle right here must be equal to 90 degrees because it's half of it then. Okay. So these are corollaries, but technically, you know, they should be theorems, I suppose, because it is provable, and we just kind of proved them right there. All right, now let's go ahead and look at some problems that we can run into, and we're going to look at more proof-based ones because the algebra one, they're not really too interesting. I want to be able to do a little bit more with these if possible. Okay. All right, so here, number one, this is actually a theorem that is in one book, but unfortunately is not in the other, and it's a pretty useful one. So this is what we call earlier the tangent secant theorem. So once again, you can see that you have a tangent line, and then you also have a secant line. Remember, by definition, secant means that you have a line that contains a chord, so 2 points that's on the circle, whereas a tangent line is supposed to intersect the circle at only one single point. So our tangent is going to be AB over here because your point of intersection or point of tangency is at A, but whereas AC over here, the line, that is going to be your secant. What I want to do is I want to prove that AC, the arc, right? So if let me go ahead and kind of highlight that part. So I want to prove that AC, the arc right here, is going to be equal to half of the measurement of angle CAB. Now, angle CAB right there is going to be this guy right here. Okay, so this looks like an IAT situation here. But the tricky part is, well, we don't actually have an inscribed angle because, well, AB is not going to contain all of, AB, the side, is not a chord that is going to be on the circle then. So let's go ahead and see if we can do a proof for this one. Okay, so what we're going to do is for this part, and by the way, when you do this one, you're not going to have to prove something this difficult. So I'm going to go ahead and do it for you just to make it a little bit easier. What I'm going to do is I'm going to go ahead and introduce the center, which we'll go ahead and P because that's what we normally use. Now, from there, what I will do is create the radii as we normally would. So this part right here and this part right here, those are going to be my radii then. And since they're radii, then that means that they are congruent to each other. Now, focus, once again, we need to show that arc AC is going to be equal to twice of CAB. So let's go ahead and introduce some variables. Let's go ahead and say that this angle right here for the arc is going to be x then. So that's this guy over here. Now, what I want to do is I want to see how x is related to all of this guy. So we're going to have to kind of start moving inward. So let's see here. Let's go ahead and say, because we have an isosceles triangle inside, let me go ahead and call this angle R, and let me go ahead and call this angle R right here. So angle PCA is going to be R, and then angle PAC, that's going to be R. So that tells me that this angle right here is going to be 180 minus 2R, because the interior of the angles adds up to be 180 degrees. Okay. Now, if you're wondering, well, why do we need that? Well, the reason is, if you now look at our picture, which looks like the following. Here, this part is going to be 180 degrees minus 2R. And then here, this part right here, that is supposed to be X. Well, that 180 minus 2R, that's the central angle to the arc of X. So what that means is those two should be equal to each other. So let me go ahead and write that down then. So 180 minus 2R is equal to X, because one is the central angle and then the other one is the corresponding arc. They are supposed to be congruent to each other. Now, let's see here. This is now the connecting factor here that I'm looking for. Look at PAB, okay? Look at PAB, which is located right here. Remember that that is supposed to be a tangent, so that tells me that this is supposed to be equal to a 90-degree angle. So what that means is this angle that I'm trying to solve for right here, which I'm going to denote as question mark, and I'm trying to solve for it, that is supposed to be equal to 90 minus R, okay? That is equal to 90 minus R. So now let's go ahead and put it all together. What I'm trying to solve for is 90 minus R, and I know 180 minus 2R is equal to X. So let's go ahead and get that 90 minus R on the left-hand side by extracting out or factoring out a 2. So 2 times 90 minus R is equal to X. So 90 minus R is equal to X divided by 2. And hey, there you go. By our substitution, what I'm trying to solve for, the question mark, since 90 minus R is equal to X divided by 2, there is going to be your proof then. Okay. All right, so that is the more difficult one. Now, let's go ahead and look at this other guy over here. Prove that CD is the geometric mean between AC and CB. Prove that CD right there, okay, is going to be the geometric mean between AC and CB. Well, the only time that we've seen a geometric mean setup is if we have a right angle, a right triangle to be a little bit more specific then, and looking at the altitude of a right triangle. So if you can somehow say that this is going to give, if you can somehow show me that we have ACB is a right triangle, then we're pretty much good to go, where C is going to be the right angle. And we definitely have that because according to our corollary, the third one right here, this guy right here, from here to here, that is a semicircle. And it's a semicircle, which means that's 180 degrees. So therefore, angle C is going to be at a right angle. And now that we have that, then that means that CD is the altitude to the AB, which is going to be our hypotenuse. So therefore, we can use that theorem from back then, which says that CD is supposed to be equal to the geometric mean, my M looks nasty, of AB then. Okay? All right. Now, let's go ahead and look at the last case over here. This one has the following then. I want to prove that angle X, which is located all the way out here, is equal to the average of those two intersecting arcs. Okay, I want to prove that angle X over there is supposed to be the average of the two intersecting arcs that it's going to contain inside. So A and B over there. So, just to kind of like, show numerically, if I have an arc right here, and if let's say that this guy right here is going to be 50 degrees, and if I say this guy right here is equal to 20 degrees, then this arc, this angle right here, and careful, this is not going to be an inscribed angle, is supposed to be the average of the two. So that means 1/2 multiplied by 50 plus 20, so that's equal to 35 degrees then. But anyhow, let's go ahead and see if we can prove this guy right here using what we know. Well, first, I would like to be able to, start showing some inscribed angles, so then that way we can go ahead and use the theorem. So the question is, how do we show these inscribed angles? Well, I can definitely do the following then. Let me go ahead and create a line segment that goes from here to here. And right there, right in this corner, you can see that that's an inscribed angle. And according to IAT, then it should be A divided by 2. And similarly, if I go to the other side over here, This angle is going to be the inscribed angle of angle B then. So that means that this is going to be B divided by 2. Now, let's go ahead and link those three things over here together. You'll notice that in the triangle, the blue one, and then the blue one over here, which I'm going to go ahead and isolate, there's the triangle that I'm talking about. This is supposed to be B over 2 over here, okay? And then this guy over here is supposed to be A over 2 over here, and this guy is supposed to be X over here. I do believe that we have an exterior angle theorem that we can work off of, which says that A over 2, the exterior angle, is equal to the sum of its remote interior. So then that means it's equal to B over 2 and then plus X, okay? And so finally, we can go ahead and I guess move one over to the other side. So that means that A over 2, let's see, it is, minus B over 2 is equal to X. And hey, guess what? It looks like I proved it, but unfortunately, I wrote down what I'm supposed to prove incorrectly. So it looks like it's going to be the difference of the two numbers then. So going back to my previous example over here, where I said that if this guy is equal to 50 and this guy is equal to 20, then that means that this guy is going to be 1/2 multiplied by 50 minus 20. So then that means it's equal to 15 degrees then. So I do apologize for that. It happens once in a while, you know, gets to the best of us, unfortunately. Well, thank you so much for watching. I will see you guys next time then. Have a good one. Bye.